Hi, my name is Eric Lassiter, and I'm going into my junior year at UNC. And this summer, I spent my time working in a neurology research lab, doing research on head injuries and Alzheimer's. The course that I would like to mentor most for this semester is Chem 261 Organic Chemistry, because I mentored for 101 this past semester, and I really enjoyed the opportunity to help the students, and the material in Orgo 1 and 2 really have interested me a lot, and I think I'd be really good at helping students, and I succeeded pretty well in the courses, so I'd love to pass on some knowledge to incoming students.
So in this problem, we're going to be looking at the acidity of various organic molecules and comparing the two. So let's look at the first one. We have a carbon with 3 chlorines bonded to it and a carbon with 1 chlorine bonded to it. The most acidic and the one with the lowest pKa is going to be the first one, because when we remove this hydrogen, the negative charge that results on the carbon is more evenly distributed between the 3 chlorines than it is on the second molecule, where there's only 1 chlorine to distribute the molecule, or distribute the negative charge across the molecule. So electronegativity is the main factor determining here. The second one, we need to look at resonance contributors. So the first molecule, we have an sp3 hybridized carbon here. So therefore, the lone pair on this nitrogen cannot resonate onto this molecule, because we know that we need a unhybridized p orbital in order to have a resonance structure. When we look at the second one, we have a resonance structure when we remove the proton, in which we can take one of the lone pairs that's on this nitrogen and we can resonate it into this benzene ring, and therefore produce multiple resonance structures that stabilize the molecule. So we would end up this structure looking something like this. And then again, this lone pair could move farther around the ring. So now when we look at this third example, number 3, number these for simplicity, we have to look at the size of the molecule. You might be likely to jump to the conclusion of electronegativity, that chlorine is more electronegative, so it's going to be the most acidic. But actually, bromine is more acidic, because the molecule has one whole extra shell in it, and that causes the bond length to be greater in hydrobromic acid than hydrochloric acid. So because the bond length is greater, it's going to take less energy for a base to come and remove this proton. So therefore, the most acidic is going to be the first. And that one's for that. Now the fourth example, we're looking at an amide and a carboxylic acid. So we need to look at the conjugate base of both of these. So I'm going to go ahead and draw those out after removing one of the protons for both of these. And we see that we result with a negative charge on a molecule adjacent to the carbonyl. So they both have a resonance structure in which we can push electrons towards the carbonyl and move electrons up to the oxygen at the top. And we result in a negative charge on the oxygen there. And a negative charge on the oxygen up here. So what are we going to look at then, since they both have 2 resonance structures? Well, the most acidic is going to be the carboxylic acid. And the reason why is these 2 resonance structures are equal contributors. As we can see, the negative charge is distributed between 2 separate oxygen molecules in this one, whereas with the amide, the negative charge is distributed between an oxygen and a nitrogen, which have different electronegativities. The electrons would rather be on the oxygen because of the greater electronegativity, so therefore the major contributor is going to be the lower example, whereas both of these are major contributors for the carboxylic acid. So therefore, we have two major contributors for the carboxylic acid, whereas we only have one for the amide, which is therefore going to make the carboxylic acid more acidic. And that's an overview of acidity.